Now we're going to take a look at the product rule for differentiation. So this is the second differentiation rule that we need to be able to prove. This is a little bit trickier. Alright, so this says if f is two functions multiplied together, then to differentiate it, it's a little bit more complicated. It's u by the derivative of v, so u by the derivative of v, plus v by the derivative of u. So plus v times the derivative of u. So once again, we're going to remind ourselves what f dash x is. So f dash x is the limit as h tends to 0 of f of x plus h minus f of x all over h. So again, back to first principles. So we're going to fill this in as we always do when we're differentiating from first principles. So let's find what f of x plus h is. We build up the top line, then we build up the fraction, then we take the limit. So f of x plus h, we simply take this, and everywhere where we have an x, we're going to replace it with x plus h. So we get u of x plus h times v of x plus h. Okay, so that's grand. Next line, so f of x plus h minus f of x. So that's the whole top line in our formula. It's going to be f of x plus h, which is this thing. So u of x plus h times v of x plus h minus f of x, which we said was u of x times v of x. Okay, grand job. So the next thing we do is we divide that by h. So it's, and we'll probably keep these separate. So let's get u of x plus h times v of x plus h. Or maybe we'll leave them as they are for now, and we'll separate them out in a minute. Alright, so that's what we get. Grand job. And the very last thing we have to do is take the limit of that as h goes to 0. So f dash x is the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's equal to the limit as h goes to 0 of u of x plus h times v of x plus h minus u of x times v of x all over h. Okay. Just while I think of it, a little comment there, it's just worth mentioning. U bracket x and u are the same thing. I should have mentioned this at the start. This is saying u is a function of x, so u depends on what x is. If you give me a different value for x, I'll sub that into u and I'll get different answers. So I've written u of x here. I've just left out the bracket x here. I could have written u bracket x here if I wanted. I just left it out. They're the same thing. This is just kind of a shorter way of writing u of x. Okay, so there's no difference between u bracket x and the u there. They're the same function. So if that's x squared plus 3, that's x squared plus 3. Okay. So back to here. Right, the problem here is if we let h be 0, this thing, so if h equals 0, this thing here becomes u of x, this thing becomes v of x, if h is 0, x plus 0 is just x, and this is still minus u of x times v of x over 0. Okay, and ux times vx minus ux times vx is just 0. The problem there is that 0 over 0 is indeterminate. If I had 1 over 0, I'd know that the limit simply doesn't exist. If I had 7 over 0, if I had minus a half over 0, the limit simply wouldn't exist. But 0 over 0 is a problem. It's what's called indeterminate. This means I don't know whether the limit exists or not. So I have to do a bit more work. So this is why this one is a bit more awkward. So what we're going to do is we're going to add and subtract a term. Okay, and we're kind of thinking towards the answer that we want to get. Okay, now the answer that we want to get is u times a derivative of v plus v times the derivative of u. Okay, now remember the derivative of v is going to have a v of x plus h minus v of x over h. That's what this is going to be. Alright, the limit of that thing. So looking down here, we have a v of x plus h here, and we'll want a minus a v of x, right, which is great. but we want to be able to factor out something in common, and we can't factor out anything at the moment. So if we do it, it might make it a bit clearer. What we're going to do is we're going to minus the term here that's going to be helpful to us. So we want to have a v of x, with v of x plus h, we want to be minusing v of x, but we want to be able to factor out a common term, so we're just left with the vx plus h and the vx. So let's multiply this by ux plus h. Okay, so I'm taking away u of x plus h times v of x. Now if I'm going to take that away, then I had also better add it on so that I don't change my answer. So I better add on u of x plus h times v of x. And remember, I still have this other blue term here, so minus u of x times v of x. And the whole thing, I'm going to put a bracket on that, the whole thing is divided by h. Okay, that's my whole top line. So I took this away because I can now factor out ux plus h from both of these, and it'll leave me with vx plus h minus vx all over h, which is going to give me the derivative of v. That's great. Hopefully the second term will take care of itself. So we're going to think of these first two as going together. So that's going to be the limit as h tends to 0. So let's factor a ux plus h out from them, and we get v of x plus h minus v of x, and the whole thing is divided by h. Oops. So taking these two together, alright, I factorized the ux plus h out from there and there, and I'm left with vx plus h minus v of x, and don't forget that the whole thing is divided by h. Alright, that's the first term. Now I have a plus here, so I'm going to put in a plus. I'm going to take the limit of the second half. Alright, so what's common here is the v of x, and that's great, because this one's going to hopefully give me ux by the derivative of v. So this one should be giving me v of x by the derivative of u. So the v of x there is common, so let's take the v of x out. And I have v of x times ux plus h minus u of x. And remember, the whole thing is divided by h. Okay, sorry. So we're going to consider each of these two halves separately. Alright, there's only another line or two. As h tends to 0, what we're going to do is we're going to kind of think of this bit as being over the h, right? We've two things multiplied, divided by h, so I can either think of this being divided by h or this being divided by h. I'll think of this being divided by h because that's what gives me, that is the derivative of v. And down here, I'm going to put the h under the second term again because this is going to be the derivative of u. Alright, so pretty much one more line and we're done. So that first term there, well, let's take the limit of the bit outside the red bracket. So as h goes to 0, this thing just becomes u of x. So it's u of x times the limit as h tends to 0 of vx plus h minus vx over h. Alright, and this one plus, now as h goes to 0, vx is still just vx. So it's vx times the limit of this bit. So ux plus h minus ux all over h. And now we really are finished, because this is u of x times the derivative of v. So that's u of x times dv dx plus, this is v of x. Sorry about that. So this is u of x. This is u of x times the derivative of v plus v of x times the derivative of u. So v of x times dx. And we're done. So just to remind ourselves what we did as ever, we constructed f dash x from first principles. The problem was it was indeterminate. So we added and subtracted something, and looking at the answer, we wanted v of x plus h take away v of x. But we needed to be able to factor out a common term, so that meant we need to have minus ux plus h times v of x, so that we can factor out the ux plus h. Alright, because up here you see we can't factor out anything from these two terms, they have nothing in common. So because we're minusing that, this red term, we better plus it as well so that we don't change the fraction. And because, you know, someone spotted that this is what happens is when you plus it as well, there's a Vx common here, and when you take out the Vx, what you end up with in the middle is ux plus h minus u of x, which is excellent because that's going to give us the derivative of ux. Take the limit of each of them separately, and we're finished.